Hello students, welcome back to our class on second Sem Hons Practicals. We had plotted a few solutions of first order differential equations, and in today's lecture we will plot the solution curve of second order ordinary differential equation. We will also plot the family of curves represented by second order ordinary differential equation. Together with that, we will also see the growth and decay models, okay, and how to plot them using SageMath. Okay, so let us just have a look. This is the problem number 15. To plot the solution curve of the second order differential equation, twice d square y dx square minus 5 dy dx plus twice y equal to 0 with initial values y of 0 equal to 0, y dash of 0 is 1. Okay, so just I have given some initial values. So so in theory we may write this part. The auxiliary equation is twice m squared minus 5m plus 2 equal to 0, okay, which is a very well known method of solving, so which gives m equal to 2 and half. Okay, so the solution is y equal to c1 e to the power twice x and plus c2 e to the power x by 2. Okay, just let me maximize so that you can see. Yeah, the auxiliary equation is twice m square minus 5m plus 2, which gives m equal to 2 and half. So the solution is y equal to c1 e to the power twice x plus c2 e to the power x by 2. Okay, and then we obtain the solution using the following Sage code. Okay, this is the Sage code. So first of all, we define the independent variable x, and then we define the function y equal to function of x, and then we just use this command de solve. So it's 2 star diff y x comma 2. So y x comma 2 represents the second order derivative. Okay, minus 5 star dy dx, okay, plus twice y comma y. So since y is the dependent variable, so this is the format for writing the Sage code. Okay, so just let us run this and see what happens. Okay, so if I just run it, shift enter, so immediately I'll get the solution. Okay, so this is the solution: k1 e to the power twice x plus k1 e to the power twice x plus k2 e to the power x by 2. Okay, so it's this is exactly the solution that we were talking about: c1 e to the power twice x plus c2 e to the power x by 2. Okay, so the same thing that we have got. Okay, so now we have to plot this particular function. So let's say yeah, so but I have not put the initial values, so let me put the initial values as well. So how to put the initial values, we have already seen how to put it. We have to write it within square brackets. So at x equal to 0, the value of y is 0. Okay, this was the initial value. Y of 0 is 0 and y dash of 0 is 1. So it's 0 comma 0, and the y dash we have to put it here. Okay, so 0 comma 0 comma 1. Okay, so this will give us the initial values. Okay, so let us run it now again. So the solution is 2 by 3 e to the power twice x, okay, minus 2 by 3 e to the power x by 2. Okay, this is the solution. Next we will plot this solution using this plot command, which is also known to you. Okay, so let us see how to plot this. Okay, so we are plotting it from x equal to minus 2 to 1. Okay, we will try with some other values as well to see how the graph looks like. Okay, so it looks like this. It's mostly exponential. It's the sum of the linear combination of two exponential functions. Okay, so the graph will be similar to the exponential curve, right? Say let us try it from minus 2 to 2. Okay, so then what happens? So this is the graph. Okay, so you can see, so at x equal to 0, the value of the function is 0. Okay, so this way you get. Okay, now let us try to plot the family of curves represented by the same ordinary second order differential equation that we have already considered in problem number 15. Okay, so this is the problem number 16. So to plot the family of curves represented by the second order differential equations, 2d square by dx square minus 5d by dx plus twice y equal to 0. So the initial part is exactly similar, variable x, y equal to function of x, then d solve of this, so we will get the expression. Okay, the next part is we have to plot the family of curves using the following Sage code. Variable x p equal to empty graphics, so we will define an empty graphics and we will solve it for we will plot it for various values of k1 and k2, that is the constants. Okay, so we will require two for loops because we have two parameters here. So for k1 in s range minus 1 to 2 comma 1. Okay, so many of you are having doubt what is s range. Okay, so I told you several times, s range minus 1 to 2 comma 1, this means the set of all those numbers which start with minus 1 and then increment themselves by 1 and go up to something less than 2. Okay, the exact value 2 is not attained, right? So s range of minus 1 2 comma 1 will mean the set minus 1. Okay, the first value will be minus 1, the second value will be minus 1 plus 1, the number that we write at the last, this is the increment. Okay, so the second value will be minus 1 plus 1, that is 0, the third value will be minus 1 0 plus 1, so that is 1, and the fourth value will be 1 plus 1 2, but 2 is exceeding this upper limit. Okay, or the 2 is actually attaining the upper limit, so that will not be considered. Okay, so s range from a to b with increment h will represent the set a plus h, a plus twice h, a plus 3h up to a plus n minus 1 into h, where this last term is strictly less than b. Okay, so similarly for k2 in s range minus 3 to 3, so what does this mean? K2 will start with minus 3, the next value that it will take is minus 2, because minus 3 plus 1 is minus 2, then it is minus 2 plus 1, that is minus 1. Okay, the last value that it will take is 2, not 3. Okay, the upper limit is not considered. Okay, so this is what is happening. So for k2 in s range minus 3 comma 3 comma 1, f of x is k1 e to the power twice x plus k2 e to the power x by 2. This is the solution that we had already obtained, and so p will be equal to p plus plot of fx comma x goes from minus 2 to 2. We are plotting the function from minus 2 to 2. Okay, so let us have a look here what is happening. Okay, so once we press shift enter, okay, so this is the plot that we obtain. Okay, so which part represents which part, you can understand by just modifying these things. So let me write it from say for k1 in s range of minus 1 to 0. Okay, that means I am considering k1 to be only minus 1. Okay, then let us see which part is represented by k1 is minus 1. So for k1 equal to minus 1, yeah, this part. Okay, the part that goes below the x-axis is represented or corresponds to k1 equal to minus 1. Okay, there were 3 parts we have already seen, so this part is clear. Let us increase the value. For k1 equal to 0, which part appears? Let us see. So for k1 equal to 0, this part appears. Okay, the almost horizontal part, right? For k1 equal to say 2, so that means I have to write it up to 2. Okay, so sorry, for k1 equal to 1, 2 means it will go up to 1. Okay, so this part, the part that goes rises above the x-axis. Okay, that part represents k1 equal to 2. Okay, right, so that in this way it continues, right? Let us try it with some other value as well. So let us increase the value. Say k1 will be considered up to 2. So in that case, what you get? Okay, so the extra part that we are getting here, this part corresponds to k1 equal to 2. Okay, so that way you can plot the family of curves. Okay, so let us keep it only up to this this one, minus 1 to 2. That means we are considering only 3 values of k1, minus 1, 0 and 1. Okay, and we are considering values of k2 from say minus 3 to 4. So we are considering values minus 3, minus 2, minus 1, 0, 1, 2 and 3. Okay, these 7 values we are considering, right? Just keep it that way. Okay, so this also you can draw, or if you want, you can just reduce the number of values of K2 if it is too difficult to draw. So K2 ranges from say -2 to 2. Okay, so in that case you will get less number of curves here. Okay, so this is the solution curve, right? Okay, so problem number 17, to plot the family of curves represented by the second order differential equation d square by dx square plus y equal to 0. Okay, so here also the solution is similar, variable x, then y equal to function of x, and then d solve diff y x comma 2 plus y comma y. Okay, so as you know, this solution will be a cos x plus b sin x. Okay, so it's k2 cos x plus k1 sin x, and then we plot the family of curves using the same system that I told you. So here we are considering only k1 in s range of -1 to 2, that is -1, 0 and 1 only. Okay, and k2 in s range, same s range. Okay, and we plot the function fx from x equal to -pi to pi. Okay, so let us see how this runs. Okay, so this is the one, so shift enter. So this is the curve that we get. So it's sin x plus, ultimately it's a sin x plus b cos x type of curve. Okay, so you will get this type of symmetric pattern, right? Because we are considering from -pi to pi. Okay, so you'll get sort of symmetric patterns. So if you like to play with it, say I take it from -1 to 5 here. Here also I take it from -1 to 5. Okay, you will get more such curves. Okay, right? So 5, the magnitude here will increase. Okay, because we have increased the values of k1 and k2. Okay, so k1 is actually giving the magnitude of these quantities. Okay, so let us write, keep it symmetrical, say -5 to 6 and say -5 to 6. Okay, so what we have done is this, we have kept it from -5 to 6 and -5 to 6. That means -5 to 5 actually, because 6 is not counted here, right? So let us see how it looks like. Okay, so it will take some time because we have included more values here. See, so this is the pattern. Okay, so nice sort of designs. Okay, that we can get. Okay, so you try it with it's difficult to draw this part. Okay, so you try it with less values, say -1 to 2, the values that I had already shown, so it will be easier for you to draw the things. Okay, so try it only for those values. Okay, right. So you can see for yourself, you can change the values and see, you can generate lots of patterns. Okay, right. Now another problem that I'll do is to plot the exponential growth model dx dt equal to ax. So the differential equation of the growth model is given by dx dt equal to ax, where a is greater than 0. Okay, for growth model it's a is greater than 0, for decay model a is less than 0. Okay, so we use the following Sage code with to plot the model with user defined values of a. Okay, so we will ask the user to input the value of a. Okay, so we'll start with variable t. X is defined as a function of t, and then we'll write a equal to input enter a, and x not equal to input enter the population at time t equal to 0. Okay, so initial population we are entering, and then we will assign this de solve, means the function obtained by solving this particular differential equation using the de solve command. We will assign it to some variable x or the function x itself, right? So x is equal to de solve of this quantity. Okay, and let us see what happens. Okay, so once we put this, say alt, yeah, it will ask us to enter the value of a. Say let us write a as 1.5, let's say 1.5. So and the initial population at time t equal to 0. So it just say initially the time the population was around 500. Okay, population of anything, people or any substance or whatever. So the answer that we get here is 500 e to the power 3 by 2 t. Okay, now we plot this solution. We plot the solution from t equal to 0 to t equal to 3 into log 2 by a. I have chosen this particular number log 2 by a because it represents the time after which the population will double itself. Okay, so in your differential equations course you have already done these things. So I am taking a time range from t equal to 0 to t equal to 3 log 2 by a. You can take other values as well. Okay, so I am taking these values to get a better curve here to understand the things better. Okay, so this is the growth curve that you get, right? So let me just minimize this little bit so you can see it better. Okay, so this is the growth curve. Okay, so initially the population was 500. Okay, so as time increases the population will increase because it's a growth model here. Okay, right, a is positive, so the population will keep on increasing. Okay, you can change the values of this inputs and you can just find out. Say I write 2, a as 2, this is the one, and then say initial population was say 2000. Okay, and let us see what happens. So this is the curve that we get, and let us plot this particular value or the solution. Plot the solution here. Okay, so it will show a similar type of curve. Okay, so this curve is actually famous for the growth model. Okay, so you will always get this type of exponential curve. Okay, similarly the second problem for this type of model is the exponential model, exponential decay model. Okay, so let us have a look here. The differential equation of decay model is given by dx dt equal to ax, where a is less than 0. So we use the following Sage code to plot the model with user defined values of a. Okay, so everything is exactly similar, right? And let us see how this runs. Okay, so we can put the value of a. The value of a will be actually negative. Okay, the value of a will be negative, say minus of 1.5, right? And the population, initial population, say it was around 5000. So now the population will keep on decreasing. So here I have kept the number log 2 by minus a. So this actually represents the half-life. Okay, the time after which the half of the population has already decayed. Okay, this is called the half-life. So we are plotting the curve from t equal to 0 to t equal to 3 times of half-life. Okay, so here you will get the decay model, curve of the decay model. Okay, just let me minimize this little bit, you can see it better. Initially the population was 5000, and since it's a decay model, the value of a is negative, so gradually the population decreases. Okay, so the population decreases. Okay, so this is the decay model, right? Okay, so these are the practicals for today. We will also do a few more, I think around three or four more problems we will plot using this SageMath. Then your course for this semester will be over. Okay, thank you.